Okay, guys, so today I want to review, first of all, in our do now, there are two ways to see where you have a relative max or min. We're used to the first way, the first derivative test to find extrema. But when it comes to differential equation problems, knowing the second derivative test to find relative extrema is going to be critical. But let's review the first derivative test. So this one says, suppose you have a function that's defined at some critical value c. Remember, a critical value is where the derivative is 0 or doesn't exist. I'm looking right here. Oops. If the first derivative changes from positive to negative at c, then there's a relative max there. So let's say, I'm going to call this c. So if the derivative changes from positive to negative, then we know we have a relative max. F has a relative max, not the derivative. The function has a relative max at x equals c. And let's say, that says if the derivative changes from negative to positive, I'll call this C2. Right? That means the slopes are changing from negative to positive, so then the function would have a relative min at this value C2. If there's no change in sign of the first derivative at a critical value, then there's not going to be a relative max or relative min there. Okay, so that one I think you're pretty confident with. But there's a second way to locate relative extrema. And again, this is going to come in handy with differential equations. This one says, suppose you have some x value, x sub 0, and you know the derivative there is 0. So the slope of the tangent is 0. And you also know the second derivative is positive. So you've got a curve. The first derivative is 0, meaning the slope of the tangent is 0, and the second derivative is positive, so it's concave up. That must mean there's a relative min. The second case is if you have a value of x, you know there the first derivative is 0, so again it has a horizontal tangent, the slope of the tangent is 0, but now you know there the second derivative is negative, that means the graph is concave down there, so you must have a relative max at that value, x sub 0. If the first derivative is 0, so you have a horizontal tangent, but the second derivative is also equal to 0, then the test is inconclusive, okay? But again, so if they're asking you with a differential equation problem, and we'll do examples to see if you have a relative max or min somewhere, if you know the first derivative is 0 at that point, and you get the second derivative, and that's positive, then you have this situation, you have a relative min at that point. If you know that the first derivative is 0 and the second derivative is negative, then you know you have a relative max at that point. All right, so let's jump in and do some problems. Okay, so the first one, this is 2005. They give you a differential equation, right? Basically, that's an equation with the derivative in it. First thing they want us to do is sketch a slope field at the 12 points indicated. Okay, so we have to draw little line segments that have the slope -2 times the x-coordinate of that point over the y-coordinate of that point. So I like to get rid of all the ones that are 0 first. So you already know that at any point where x is 0, the derivative, the slope of the tangent will be 0. So all the points whose x-coordinate is 0, so here's a point, the slope is 0. The slope is 0. So I'm drawing little line segments that have a slope of 0. Now the other ones we're going to have to do individually. So, and we'll just do a few of them because this gets a little boring. So let's look at the point 1, 2. There, the slope is going to equal -2 times 1 over 2. So that equals -1. So I have to draw a little line segment with a slope of -1 there. And then at the point let's do 1, 1. There, the slope is going to equal negative 2 times 1 over 1. So the slope now is negative 2. So think of going down 2 over 1. It's just a little deeper. Oops, I missed it. Oh, well, too bad. Let's see if I can grab it. Nah, I'm not even going to bother. Oh, I can grab it with this. See if I can move it over. Ah, that's kind of really too steep, but oh well. And then you'd have to go through that process, drawing these little line segments. And just so you can see what it would look like, you'd have to make sure you got all 12 of them. If they tell you 12 points, whoa. Make sure you have all 12 points. I'll just show you what that looks like. So when you're all done, this is what it should look like. I mean, it's only 2 points, but let's turn my phone down. It's only 2 points, but still, they give you 1 point just for getting the zero slopes right, like these. And then you get another point for getting the other slopes right. Okay, now we get to a good one. B. Let y equals f of x be the particular solution to the differential equation with the initial condition 1 equals negative 1. In other words, let this be the function that has that derivative that goes through the point 1, negative 1. Oh, we're not asked to find it yet. All they want us to do is write the equation for the tangent line to the graph at f of f at 1, negative 1. Oh, so the only thing we have, so we'll use point slope. This will be our point 1, negative 1. So y minus the y coordinate of the point, so minus negative 1 is plus 1, equals, now we'll get the slope in a minute, and then we have x minus the x coordinate of the point. The slope of the tangent line is just dy dx at that point. So to figure out what the slope is, remember it's negative 2x over y. So to get the slope, negative 2, so the x coordinate of our point is 1, and the y coordinate of our point is negative 1, so this comes out to be positive 2. So write the equation of the line tangent to the graph at that point. Now we're not done. They want us to use it to approximate f of 1.1. So from here, let me just move the 1 to the other side. So we have the equation of our tangent is y equals 2 times x minus 1 minus 1. And so I'm going to approximate the y on the graph by getting y on the tangent line. F of 1.1 is approximately 2 times 1.1 minus 1 minus 1. So this would be 0.2 minus 1. Now, I would leave my answer like that, but just so you guys know, that's equal to negative 0.8. Well, let me just go to our solutions. Okay, so you get 1 point for writing the equation of the tangent line, see that? And then 1 point for plugging it in and getting the negative 0.8. But again, you didn't have to simplify that. You could have just left it. Okay, part C. Let's erase some of this. Yes. Okay. This, when they ask you to actually find the particular solution, that's where most of the points tend to be in a problem like this. Okay, find the particular solution to the given differential equation with the initial condition f of 1 equals negative 1. So to get the function, the reason I'm going to have to separate and integrate, you see, look at this derivative up here. If the derivative only had x's in it, you could just integrate. You wouldn't have to separate first. So whatever the variable down here is in the derivative, if that's the only variable you see on the other side, then you don't have to do this whole separate and integrate. But if I look at this derivative, there's a y there. So that's why I have to separate and integrate. Okay, so let me just write that down. So dy over dx equals negative 2x over y. Okay, So to get the particular solution, first you cross multiply. We got to separate the variables. Y, dy, I'm sorry, I'm trying to write the best I can with this thing, equals negative 2x dx. You separate the variables, and now you're going to integrate. When you integrate, you only put the plus c on the independent variable side, so on the x side. So this side, we get 1/2 y squared. The other side, we get negative x squared plus c. Now, I think I'm going to multiply each side by 2. Now, if you want to figure out what c is now, you can, or if you want to do something else and then figure out what c is. But the important thing is, whenever you stop to put in the coordinates of the given point to get c, that's where you have to go back to. I think I'm going to multiply each side by 2. So y squared equals negative 2x squared. Now 2 times that c is just some other random. Until I find it, I can just keep calling it c if it just turns out to be another number. Okay, now let's figure out what c is. The way we figure out what c is, after you integrate, you can plug in the coordinates of the point. So I'm plugging in 1 for x and negative 1 for y. So I have negative 1 squared equals negative 2 times 1 squared plus c. So 1 equals negative 2 plus c. So c equals 3 when I stopped here. So I have to go back. Look at what I'm doing now. I'm going back to the equation right before I plugged in the numbers, and I'm rewriting that, not the one before. Oh, that'll give me the wrong answer. I'm rewriting the equation just before I plugged in the coordinates, putting in the value I find. Now, your answer to a differential equation, your particular solution has to be a function, okay? So you know normally that when you have something squared and you want to solve for, you do plus or minus. So I'm going to write that down, plus or minus. Now you have to decide which one. You got to have just one function. Well, remember, it has to go through the point 1, negative 1. So when you plug in 1 for x, you're supposed to get a negative y value. So that means the solution for this one is y equals the negative square root of negative 2x squared plus 3. So that decision you're only going to have to make when you wind up with y squared. You'll have to decide whether you want to take the positive or negative square root, and that depends on the y coordinate of the given point. I mean, it could be y to the 4th, you'd have to decide. At y to any even power, you'd have to make that decision. Okay, now let's take a look over here. See, they stopped in the answer key, they stopped a little earlier to figure out c, and then it was 3/2. But when they plug it back in and solve for y, they're still going to get the same answer. Okay? One thing I just wanted to note here, because it came up in something else I gave you guys to do, this solution had to go through the point 1, negative 1. If they had asked me to sketch the solution, I just want, this is just a little thing, but remember how the derivative was equal to negative 2x over y? Any value that makes the denominator of your derivative 0, so y equals 0, is going to be a boundary. In other words, your solution can't go past it. So when I draw, if they had said sketch the solution given this, I could just, make sure I go through the point 1, negative 1. I could just follow the direction, but when I get up to y equals 0, I'm not going to include it. And then the rest of it, oops, I'd have to do something like this. I'd follow it, but again, can't cross. So that would be what my solution would look like. They didn't ask it, but just want you to realize that any value that makes the denominator of your derivative equal 0, that's going to be a boundary for your solution. It can't cross. You want your solution to be a function here. All right, let's try another one. We're going to do parts B and C of this one. This is from 2007. All right, so this time you see our differential equation up here. Find the second derivative in terms of x and y. Describe the region in the xy plane. describe the region xy plane in which all solution curves are concave up. Okay, we know a graph is concave up when the second derivative is positive. So, well, first let's get the second derivative and then we'll see what they're talking about. So I've got to start out with dy dx equals 1/2 x plus y minus 1. That's our first derivative. The differential equation is our first derivative. All right. Now, the second derivative is just the derivative of the first derivative, but we're taking it with respect to x. So we'll take the derivative of 1/2 x. That's just 1/2. But now we get to the derivative of y. It's not just 1, it's 1 dy dx. Remember, the derivative of y with respect to x is dy dx. And the derivative of minus 1 is 0. Now, they said get the second derivative in terms of x and y. So you can't just leave a dy dx. You have to substitute in. So dy dx is equal to 1/2 x plus y minus 1. So let's clean this up. So our second derivative, if I combine like terms, is equal to 1/2 x plus y. I had a minus 1 and now I have a plus half, so minus 1/2. Now this second derivative will equal 0. It will equal 0 when y is equal to, if I solve for y in that, second, if I subtract, it would be negative 1/2 x plus 1/2. So at all the points, which would just be points on a line, where y equals negative 1/2 x plus 1/2, the second derivative would equal 0. But we want to know when the graph would be concave up. So this second derivative will be greater than 0 when y is greater than negative 1/2 x plus 1/2. That part was a little tricky on this one. Okay, let's go back now. Oh, let's look at the answers for that. Okay, part A we didn't do. Okay, so here we go. So that was 3 points. 2 of them were to get the second derivative, so that's good. Now let's go back and look at C. Erase this. Oh, actually, let me not erase. I'm not going to erase my second derivative because for C, it says let y equals f of x be a particular solution to the differential equation. That goes through the point 0, 1. Does f have a relative min, max, or neither? This is when you're going to need, when they ask me if it has a max, min, or neither in one of these differential equation problems, you're going to have to use the second derivative test for extrema. So let's first see, since they're telling us that f of 0 equals 1, let's see what the first derivative equals at that point. So the first derivative evaluated at the point 0, 1, where's my first derivative for this problem, is equal to, remember it was 1/2 x, so 1/2 times 0, plus y, so plus 1, minus 1. Oh, good, that equals 0. So we know this function, we have no idea what it looks like, but we know that the first derivative, the slope of the tangent there is 0. Now let's see what the second derivative is at that point. So we're going to plug it in. Remember we had it was 1/2 x, so 1/2 0 plus y, so plus 1, and then it was minus 1/2. Yeah, when we combine like terms. If we figure this out, we get 1/2. Now, I don't even have to say what it is. I could just say, oh, that's greater than 0. So the second derivative is positive. The first derivative is 0, slope of tangent 0. Second derivative is positive, which means you have a relative, f has a relative, since it's concave up, min at x equals 0 by the second derivative test for extrema. Second derivative test for extrema. Okay, so that will follow. A lot of times when they ask you to get the second derivative, which remember, we had to remember derivative of y was not just 1, it's dy dx. But getting it, sometimes they'll follow up by that by asking you if you have a relative max or min at some point. You got to show that the first derivative is 0, and in this case, if the second derivative is positive, you have a relative min. Let's see what they say here. Oops. So you got to show that the first derivative is 0 and the second derivative is positive. Okay, very nice. Those are the conditions you got to show. All right, we got one more here. Don't worry, it's not over yet. 2011, number 5. So in this one, at the beginning of 2010, a landfill contains, oops, let's do a little rewind on that. Oh boy, sorry kids. Okay, contains 1,400 tons. So that's the amount of landfill at time 0. Well, 2010, we're going to be time 0. The increasing function W models the total amount of solid waste stored in the landfill. Planners estimate that W, the amount of waste, will satisfy the differential equation. So here's our differential equation right here for the next 20 years. W is measured in tons, and T is measured in years from the start of 2010. So they did tell us the amount of waste at time 0 is 1,400 tons. A, use the line tangent to the graph of W at time 0 to approximate the amount of solid waste that the landfill contains at the end of the first 3 months. In other words, when T is 1/4. When they say use the line tangent, first you're going to graph, you're going to write the equation on the tangent line. So we're going to write the equation of the tangent line at time 0. Okay, and we're writing it to W. Remember, to write the equation of a tangent line, it's going to be y minus y1, which will just be the function at time 0, equals the slope, which will be the derivative at time 0, times x minus, in this case, 1/4. Oh, no, sorry, oops, pause. No, I'm not going to pause, I'm just going to erase it. X minus 0, getting ahead of myself. Red. Okay, let me say that again so that's not confusing. To write the equation of the tangent line to W at time 0, y minus y1, you get that by plugging in 0 into the function, so W of 0, equals the slope of the tangent line is, you get that by plugging 0 into the derivative, and then x minus 0. Okay, so our tangent line is y minus 1,400 equals, to get the derivative, we look at the differential equation. Now, when T equals 0, W is 1,400. So that's what we got to plug in, right? We don't plug in 0 for W. That's the waste isn't 0. At time 0, W is 1,400. So if I plug 1,400 in for W, 1,400 minus 300 is 1,100. So I have 1/5, 1/25 times 1,100. 1,100 over 25. I think that's just 44. That's x minus 0. Now I got to finish. I want to clean this up because then I'm going to plug in 1/4. Let's go down here with this. All right, so I have y minus 1,400 equals 44x, or y, this is the equation of the tangent line, equals 44 4x plus 1400. And we want to approximate the amount of waste when t equals 1/4. So we plug a fourth into that. So 44 times 1/4 plus 1400. So it's 11 plus 1400, oops, approximately equal to. So that equals 14. You know what, I'll just write W of 1/4 is approximately equal to, this is 1/4 of 44 is 11, so 11 tons. So with a differential equation, very common, they'll ask you to write the equation of a tangent line. They've given you the derivative, so they've given you the way to get the slope. But what I wanted to stress here, you're writing the equation at time 0. But in your differential equation, there's not a t to plug the 0 in. You have to use the fact that when t is 0, W is 1400. Okay. Let's just take a look at that. All right, that was worth 2 points. Now, part B, find the second derivative in terms of W. Use it to determine whether your tangent line approximation in part A is over or under. Okay, so we know we're going to have to get the second derivative. Let's write down the first derivative. 1/25 W minus 300. Okay, so the first derivative, 1/25 W minus 300. Okay, we want to get the second derivative. We're going to take the derivative of the first derivative with respect to t. So if it's not a t, the derivative is not just 1. Okay, so we have a product, but this first factor is just a constant, so we leave it. Now we're going to multiply by the derivative of 1 minus 300. The derivative of w is dw dt, right? And then minus 0. They want the second derivative in terms of w. We can't leave it with a dw dt in there. So now I need to replace the dw dt. I need to substitute in for it. Remember, that was 1/25 w minus 300. So the second derivative is 1/625 times w minus 300. Okay, so they wanted us to get the second derivative. We did. And then they want us to determine if our tangent line approximation was under or over. So we got to see if the graph was concave up or down where we drew the tangent line. So when we get the second derivative, when we evaluate it when t was 0 and w was 1400, we have 1/625 times 1400 minus 300. Well, whatever that is, I know it's positive. That means the graph is concave up. And if W is concave up, oops, right? You used a tangent line approximation to approximate a functional value where the graph is concave up. So that means your approximation is going to be less than the actual value. Just check the wording here. So is our approximation an underestimate or an overestimate at t equals 4th? So that means our approximation is an under approximation. I'll show you the nicely written out way. Okay, so if the second derivative is positive, the graph's concave up, which means the tangent line would be below the graph. We're using the y's on the tangent line for the approximation, so it's an underestimate. Okay. All right, last part. This is where it gets big now. Let me erase some stuff. sorry, just a little bit more. This is good for now. Okay, so let's go blue. Find a particular solution. So get the function W of t, W equal to W of t of this. So starting with that condition. So the first thing you have to do, you see how our derivative dw over dt, the independent variable is dt is t. And the derivative doesn't just have t's in it. That's why to solve it, I have to separate and integrate. To separate and integrate, you either multiply or divide. So I'll divide both sides by w minus 300, and I'll multiply each side by dt. So I'll have dw over w minus 300 is equal to 1/25 dt. W's on one side, t's on the other. You know, this constant, this 1/25, I like to leave it on the independent variable side because your goal is to get w by itself. So even though technically they could be on either side, it's easier this way. Okay, so now we've separated, we have to integrate. And when we integrate, we put the plus c on the independent variable side, the t side. Now look at the left side. It's a du over u. The numerator is the derivative of the denominator, right? I'll just put this to the side. Whenever you have a situation like that, you get ln absolute value of u plus c. Oops. So on this side, I just get the ln of w minus 300. The other side, I'm just integrating a constant, but now the variable is t, so that is just going to be 1/25 t plus c. Now we're trying to solve for w, so I'm going to exponentiate. In other words, I'm going to say e to this side is equal to e to that side. Oops. Okay. So on this side, now technically I would have w minus 300. Right? This side, when you have the plus c up there, it's just going to come down front. The reason is because this side would be e to the 1/25 t times e to the c. Right? When you multiply with the same base, you add exponents. So when the exponent looks like a sum, you can break it up to look like multiplication. But this e to the c is just your new c. All right. So I have absolute value of w minus 300 is equal some new c, and you don't have to write new c, times e to the 1/25 t. Now the absolute value, it's just either going to be positive or minus. So, you know, technically, some people get crazy about this. You could write plus or minus some c, e to the 1/25 c. I usually don't do it this way. I usually just say, okay, let's just figure out what c is. You'll know what it is in the end. All right, now we got to solve for c. No, we're just going to solve for c. Let's see, the point we have to use is when t is 0, w is 1400. Okay, so 1400 minus 300 is equal to some number, and I'm just going to call that number c, because, you know, you'll find out whether it's positive or negative. And then it's going to be e to the 1/25 times 0. Well, e to the 0 is just 1. So 1100 is equal to c. So now I have my solution is w minus 300 equals 1100 e to the 1/25 t. So I want to solve for w. I got to, you know, solve for my function. And when you solve for it, make it look pretty, make it look like put in function notation. So call it w of t is equal to 1100 e to the 1/25 t plus 300. That would be, oops, the particular solution. So you'll see, like if you plug in 0 for t, W will be 1400. So let's take a look at the solution here. Yeah, they just call it C. That's what I always do too, but I just want to make sure. You might be looking at other places, they'll say plus or minus. So I call it C, and I just kind of lose the absolute values here. Alrighty, and that's the particular solution. And I believe that is the end. All right, 35, 36 minutes, not so bad. So try the problem I'm going to assign you. You're going to love it.